We want to complete the computation of the transition probability of the Unruh effect. We found this formula here for the probability, we call it Pi, that the detector detects something. So let us now apply the change of variables that we wrote the other time, which is here, and that is useful to turn this denominator of the integrand, thanks to this formula, into an infinite sum, where it is clear which poles will contribute by applying the residue theorem and which will do not. We have an infinite set of poles all over the imaginary axis in this variable that we called u. Here it is, and that is related to y that way. And the contributions can only come from if we close the integration path in the upper half plane of the complex u. The upper half of the complex u plane can only come from the poles in the that are located here. So let us apply the change of variables as well as the residue theorem. Okay, so Pi is equal to what? Minus g squared omega divided by 4 pi squared ei chi0 e0 modulo squared. Then there is this integral from minus infinity to plus infinity of du. Du is g divided by 2 pi, du is dy times 2 pi over g. Then we have the exponential factor and the denominator, which will be a sum, an infinite sum. So 1 over pi squared, sum minus infinity to plus infinity, of 1 divided by y plus ik squared, and the exponential e to the I ei minus e0 times u, and that is g times u, and that is 2 pi over g y. We do not need to write the infinitesimal contribution due to epsilon in the exponent, because that is no longer needed. And now we apply the residue theorem. So what do we get? Minus g squared omega. We have 2 and 16, 8. Then we have 4 pi's in the denominator and 1 pi in the numerator, so we have pi to the cube. We have a power g also. Ei chi0 e0 modulo squared integral. Well, we can exchange now the sum with the integral, and as we said, the sum is restricted to the cases k smaller than 0. So here we have k equal to minus infinity plus infinity, and then we will restrict the sum from k equal to minus 1 to k equal to minus infinity. Okay, then we have to apply the residue theorem. Since the residues are circumvented the right way, there is 2 pi I. Then we have to apply the residue theorem in this form. So you see that the integral is equal to 2 pi I divided by 2 factorial. But 2 factorial now is 1 factorial because we are just taking n equal 1. But the important thing is that we have to compute the first derivative of the function and not just the function. So we have to compute the first derivative of that function with respect to y, and that gives ei minus e0 2 pi over g, that is the derivative, times the exponential ei minus e0 2 pi over g, and then y is equal to minus ik. Okay, so let me check the number, the factors here. Yes, okay, that's okay. So there is a factor g that goes away here, another factor g that goes away there, pi and pi cancel pi cube and leave a pi. Then there is a factor 2 that gives a 4. Then there are various factors I cancel the minus sign, so we have 4 pi in the denominator, omega in the numerator, and then we have ei chi0 e0 modulo squared. There is another factor actually that, oh, there is another factor 2 that I missed, so here we have just a2. Then there is also a factor ei minus e0, and then a certain infinite sum where we can change the sign of k for convenience, and in the exponent you have minus I times I, which is plus 1, and then k changes its sign, so we have 2 pi divided by g times ei minus e0 k. Now we can do the sum and perform summation because it is a geometric series, and we work out what we call wi, which is the probability per unit time, and that is equal to pi divided by omega. That's where we lose the factor omega, and that is equal to the infinite factor omega. That is equal to what? ei minus e0 divided by 2 pi times the modulus squared of ei chi0 e0, and then what about the sum? k equal 1 infinity, e to the minus 2 pi over g ei minus e0 k. So we can define a to be equal to the exponential of 2 pi over g times ei minus e0. That's a positive number, and that is also bigger than 1, greater than 1, because ei is greater than e0. And then we have the sum from n equal 1 to infinity of a to the minus n, which is of course equal to 1 divided by 1 minus 1 over a minus 1. And so we have 1 divided by 1 minus 1 over a, and in the numerator we have 1 over a. So the result is 1 divided by a minus 1. Okay. In the end, we get wi equals ei minus e0 divided by 2 pi ei chi 0 e0 modulo squared, and then we copy this result 1 divided by a, where we replace the formula for a, so that is equal to 1 divided by a, which is e to the 2 pi over g ei minus e0 plus 1. And that's the final result. And as you can see, this is the distribution of a black body. So it is a black body spectrum with a temperature equal to what? The 1 over temperature is equal to 2 pi over g. So the temperature is equal to the acceleration g divided by 2 pi. To summarize, a uniformly accelerated detector detects particles in vacuum with a spectrum that coincides with a black body spectrum with a temperature equal to the acceleration divided by 2 pi. At the same time, a detector that is in motion with constant velocity does not detect anything. Okay, so this is the end of the first part of the course. In the second part, we will discuss many more issues and get finally to the quantization of gravity. But before going there, we have some subjects to gaps to fill, and in these two lectures we will talk about massive fields, bosonic fields of spins equal to 1, 2, and 3/2. These are the theories of Broca, Pauli fields, and Gravita-Schwingle. and Rarita-Schwinger. So the Proctor theory deals with particles of spin 1 and a non-vanishing mass. Pauli field's theory deals with particles of spin 2 and a non-vanishing mass, and the Rarita-Schwinger theory deals with particles of spin 3/2, both with zero mass and non-vanishing mass. It's called Rarita-Schwinger in both cases. And when the mass of the Rarita-Schwinger spin 3/2 field is zero, then it is a gauge field. Same way as massless spin 1 fields are gauge fields, and the massless spin 2 field is the graviton, if you want. And the massless spin 3/2 field is called gravitino, and it is the gauge field for a local symmetry that is called supersymmetry, and that is the local version of a global symmetry. So, sorry, the local symmetry is called supergravity, and that is the local version of a global symmetry that is called supersymmetry. Supersymmetry is a symmetry that claims there is a one-to-one correspondence between bosons and fermions. So let's start with the Proctor theory. The Proctor action in gravity is as follows: square root of minus g, then you have minus 1 over 4 f mu nu f rho sigma g mu rho g nu sigma plus m squared divided by 2 a mu a nu g mu nu plus what are known as non-minimal couplings, because in gravity you can have such terms as well, and unless you go to higher dimensions you just have these two. So that means, by assuming that the constants in front of them, which are called here eta p and eta p prime, do not have negative dimensionalities in units of mass. So the Proctor field here is called a mu, like gauge fields, and precisely as in the case of gauge fields, we define f mu nu as del mu a nu minus del nu a mu. Notice that the sign here is plus and not minus. A scalar field would have a minus because the Lagrangian is T minus the potential. But here you have plus correctly, because remember that a square, we have the 4 vector here, which is contracted by means of the Lorentz a metric in the Lorentz signature, so that would be a0 squared minus ai squared, and the 2 degrees of freedom, the 3 actually, here there will be 3 degrees of freedom, as we will see in a moment, are precisely those of the space part, so to speak, and then this is the minus sign that gives the correct sign in front of the mass term. So these are called non-minimal terms. Okay. Let's see what happens in flat space. The Lagrangian is just the usual Yang-Mills Lagrangian, which is minus 1/4 f mu squared, or minus 1/2 del mu a nu times del mu a nu minus del mu a mu, plus m squared divided by 2 a mu a mu. So let's check the field equations. Box a mu minus del mu del dot a, the usual part, and then there is a correction due to the mass. That is m squared a mu. That is equal to 0. If we take the divergence of this equation, we have box del a minus box del a plus m squared del a equals 0, which implies what? Del dot a equals 0, and when del dot a is equal to 0, what we get there is that the box plus m squared a mu is also equal to 0. So basically this condition takes 1 degree of freedom away, and we remain with 3 out of 4, and 3 are precisely the degrees of freedom, the components of a spin 1 field, a massive spin 1 field. So not only 2 helicities, when the mass is 0 you just have 2 helicities, 2 degrees of freedom, but the mass is non-zero here, so you have 3. Let's check the propagator. So the quadratic part of the Lagrangian in Fourier transform is a mu of p times minus p squared del eta mu nu. So when you use an integration by parts, there you have you cancel this minus, and then you have a box, but a box is minus p squared in Fourier transform. So that's correct. Then you will have p nu plus m squared eta mu nu times a tilde nu of p. So we have to invert this operator, eta mu nu times minus p squared plus m squared plus p mu p nu. What is the propagator? The propagator will be denoted like that. I write the result and then we check that it is the correct one. Minus I divided by p squared minus m squared, there is a minus, eta mu nu minus p mu p nu divided by m squared, which we call I p mu nu. And so we have to check that this matrix p mu nu contracted with q nu rho will give the identity. Let's check. So p mu nu is 1 divided by minus 1 divided by p squared minus m squared times eta mu nu minus p mu p nu divided by m squared. And that has to be multiplied by this. So minus p squared plus m squared eta nu rho, we have to raise an index, so that is delta nu rho, plus p nu p rho. Okay, let's check. If we multiply these two, we have an eta minus p squared plus m squared divided by p squared minus m squared and multiplied by minus sign gives 1. So that will be eta mu rho. Then we can check what we obtain when we multiply. So far we have multiplied this times this. What happens when we multiply that times that? 0, because there is a contraction P with this object which is transverse, and the contraction will give 0. So basically we have already multiplied eta mu nu by both, and what remains is just to multiply that by both. So we will get plus, so minus and minus will give plus, 1 divided by m squared, which is this m squared, p squared minus m squared, oh sorry, no, this is not transverse. It's not transverse because this is not p squared. That's transverse when we have a massless field. So there is a contribution coming from this object. So let's check that contribution first. So we multiply, let's recapitulate, we have multiplied these two, and now we multiply these two. So that will give minus 1 divided by p squared minus m squared times p mu, p rho. And finally the term that we were writing before, that is equal to plus 1 divided by m squared p squared minus m squared, and then we have a p mu that stays out, p mu, p rho times minus p squared plus m squared, and then p nu plus p squared p rho. Okay. Okay. Now let's check these objects. Here there is already a simplification because we have minus p squared p rho plus p squared p rho. And here we remain with p rho m squared divided by m squared as p rho. So p mu p rho divided by p m squared minus m squared cancels that precisely, which means that this is equal to eta mu rho, as we wanted. Another property is that pi mu nu contracted with pi nu gives what? We have already done it inside this calculation, but let's do it again. So we just ignore the I. Minus 1 divided by p squared minus m squared. Then we contract this by pi nu, which is not 0, as it would be in the case of gauge fields, because in those cases we have a p squared there, and then we have a gauge fixing parameter multiplying. But what do we get instead? We get p, so we contract by p nu, yes, p nu, so here we get p mu, and there is a p mu there also, so we can collect a p mu, and we get minus 1 minus p nu will give p squared divided by m squared, and that is equal just to p mu divided by m squared. So what does it mean? What is the meaning of this calculation we have already done? The meaning is as follows. You see that this propagator has a pole, but the contraction doesn't have a pole. So that means that not all 4 components of the field do propagate indeed, because one of them is killed, because the divergence, classically you see it like that, the divergence is identically 0 by means of the field equations. So there is no divergence propagating. Here is the same, because when you take the divergence of the propagator, which means that you contract the propagator with the momentum, you cancel the pole, because the pole is cancelled by that factor, and so you do not propagate anything. But we can be more precise here. So let's check that on the pole, p squared minus m squared, we can choose p mu equal m 0, 0, 0, because this is a massive field, so it can be at rest. And then let's check the residue of the pole on the pole. So apart from the minus sign, we have eta, so that will be 1, minus 1, minus 1, minus 1. And then you have this thing. What is this thing? Well, p mu has only a component 0, p0, because the others are all 0. So you have only a contribution here from mu equals 0, mu equals 0. The component 0, 0 will be minus m squared, because p0 is m squared divided by m squared, so minus 1. And that is our result. You see that you have 3 components, 3 propagating degrees of freedom. All of them have correctly a positive residue at the pole. Now we move to the Pauli fields. Chi mu nu is a symmetric tensor . It describes a massive spin 2 particle, so in the end it will propagate only 5 components, because spin 2 has 5 components. 2, 1, 0, minus 1, minus 2. But we start with a 4 times 4 symmetric tensor. That means 10 components. Now, if you consider its divergence, del mu chi mu nu, that's a vector. So you can say that's a 4 vector. You can say that that is a vector, a 3 vector, plus a scalar. That scalar could also be seen as this double divergence. So we will lose this for these 4 components, but 4 is not enough. 10 minus 4 is 6, and we want to get to 5. And the 5th one is the trace. So that is also a scalar, a different one. Basically, in the end, we will have only 5 propagating degrees of freedom. forgot something here now. Forgot to mention one property that we are going to use here. But before using it for Pauli-Fierce fields, we wanted to check it with Broca fields. And basically what we want to do here with spin-2 fields is something that we want to explain the Pauli-Fierce fields in a slightly different way with respect to what we use with the Broca fields, because in the case of the Broca fields we could start from the action. It was easy to guess what the action was. Well, if you want, it's possible to do the same procedure for Pauli-Fierce fields. But it's not that smooth. There is another procedure that we can use with Broca fields, and first we describe that one, and then we go on to the Pauli-Fierce fields by means of a similar procedure. What is this procedure? So with Broca fields, we can also get to the right action from the propagator. We can also start with the propagator. We can also ask ourselves what must necessarily be the propagator of a massive spin-1 field. And to do that, to answer the question, you have to build the most general P mu nu. So instead of knowing the answer already, starting from the answer, we build the most general P mu nu with a pole in P squared equal to M squared, but such that P nu has no pole. So you start from the most general formula. What is it? By Lorentz invariance, so you have a pole, but then what you can put there is there are only two terms, A, constant A times eta mu nu, plus a constant B times P mu P nu. There's nothing else you can do. Okay, now we demand that this contraction has no pole. And what does that give? A P mu plus B P squared. The residue at P squared equal to M squared should be 0. And that means A plus B P squared equals 0 for P squared equal to M squared. And that gives B equal minus A divided by M squared. P mu nu is then equal to the constant A, which we can collect, divided by P squared minus M squared times eta mu nu minus P mu P nu divided M squared, divided by M squared. So you see, this is the unique propagator. Then you can normalize the field the way you like. You can invert the propagator, so you get Q. Q is the quadratic path of the Lagrangian, and so you get the Lagrange. This is the inverse path. Still, it's unique. There is nothing else you can do. By the way, observe that this is a normal term for the propagator, but this one has a bad power counting, because for large momenta it doesn't fall off like 1 over p squared. This increases like p squared divided by p squared. So it's p squared divided by p squared. So there is one component here that gives trouble with renormalizability. This is a non-renormalizable term. And we must take care of that. The Proctor theory is not a renormalizable theory. There is little to do about it. So, with the Pauli fields, you can proceed the same way. You search for the most general propagator that does not propagate these two sets of fields. And there will be only one, and that will be the propagator of the Pauli fields, and when you invert that propagator, you get the quadratic Lagrangian, and so on and so forth. So the propagator will be now an object with 4 indices, p, mu, nu, rho, sigma, because it has to propagate, has a 2-point function, chi, mu, nu, chi, rho, sigma, if you want. So it has to have 4 indices. And that will be equal to something like 1 divided by p squared minus m squared, times something. And what are the properties that it should fulfill? First, it should be symmetric in the exchanges of mu with nu, rho with sigma, because chi mu nu is symmetric. And also if you exchange the pair mu nu with the pair rho sigma. These are the symmetric properties. And then it should also satisfy the condition that it doesn't propagate anything more than the 5 components you expect from a spin 2. In particular, and the result will be that it will be uniquely fixed. So it is uniquely fixed by what? By these 2 extra requirements, which are that the contraction with a trace and the contraction with a p have no poles. That is the requirement. So I will just give you the answer and check that it satisfies the requirement, because it is a bit long to do the other way around. But it is possible to reach it by following the recipe that I just given you. So p mu nu rho sigma will be equal, if I include the I here, that is the complete propagator with the I factor, I divided by 2 times 1 divided by p squared minus m squared times pi mu rho pi nu sigma plus pi mu sigma pi nu rho minus 2/3 pi mu nu pi rho sigma, where pi mu nu is the object we have already met in the Proctor case, eta mu nu minus p mu p nu divided by m squared. Let's check now that this propagator fulfills the requirements. The symmetry properties are okay because it's symmetric in the exchange of mu with nu, rho with sigma, and the pair mu nu rho sigma. with rho sigma. To check the other two properties, let's first compute the trace of this small pi, and that trace will be equal to 4 minus p squared divided by m squared. Let's also compute the contraction of two pi's of the product, which is pi mu nu pi nu rho. That's eta, so it's like the square of the two, minus pi minus p mu p rho divided by m squared, minus 2 because there is a double product there. And finally, there is the square of the second term, which is equal to pi mu pi rho p squared divided by m squared. Now, you can easily see that that this is equal to pi mu rho plus something that vanishes on shell. Why? Yes, there is an easier way to show it. Let me show it this way. Let me check also the simple contraction pi mu nu p nu, which is equal to p mu times 1 minus p squared divided by m squared, and that is 0 on shell. And so you also have this conclusion here because what is the square? Pi mu nu times pi nu rho. Check the second, pi nu rho. Pi nu rho is 1 plus something that gives 0 on shell by this contraction. And so the product of two pi's is 1 pi plus something that gives 0 on shell. Therefore, first check pi mu nu rho. Rho has no pole. That means that if we have there a contraction, let's begin with this, which is easier. So first, this is easier because every time we contract a pi nu sigma with p sigma, pi mu sigma with p sigma, pi rho sigma with p sigma, we find something 0 on shell. So this is obviously 0 on shell. Sorry, this is obviously finite on shell. Has no pole. This is the right way of phrasing it. Has no pole on shell. There's no pole. Sorry. Obvious. And instead we have to work a little bit, not too much, to show that this has no pole as well. How to do it? So when you contract rho with sigma, you can replace pi pi time with a pi, because we can neglect the things that are 0 on shell. So we have 2 pi mu nu plus something that vanishes on shell. Okay, Then there is the same here, and that is minus 2/3 pi mu nu times that trace, 4 minus p squared divided by m squared. And that gives what? I pi mu nu divided by p squared minus m squared. We collect pi mu nu. And we divide by 2, just to simplify a little bit. So we have 1 minus 4/3 plus 1/3 p squared divided by m squared, and plus no poles. This is order 1. And you can see 1 minus 4/3 is minus 1/3. So precisely you cancel the pole and you have something of order 1. Now, once you have the propagator, and again, as I said, you can prove that this is unique apart from the constant in front, which you then normalize. First, you know what the sign of the constant is, because the residues have to be positive. But apart from the sign, the constant is arbitrary, so we just chose a standard normalization here. Once you have the propagator, you can invert the propagator and you can work out the Lagrangian, the quadratic part. And then you can covariantize the quadratic part and you get the Lagrangian of the massive spin-to field coupled with gravity. So this is the Pauli field's action. 1 divided by 2 integral of square root of minus g del rho chi mu nu del rho chi mu minus del mu chi del mu chi. Chi will be the trace, but the contraction is calculated with the metric g mu nu. Then you have plus 2 del mu chi del mu chi mu nu plus minus 2 del mu chi nu rho del rho chi mu nu minus m squared chi mu nu minus chi squared. And if you want, then you can add non-minimal terms. We will list them in 10 minutes.